evening to one and all. On behalf of IIT Madras and the Office of Global Engagement, it is truly my great pleasure to welcome you to the Eminent Speaker Lecture Series. We are truly honored that you chose to be today here this evening to what promises to be an intellectually stimulating and inspiring lecture. So before we begin, I would like to request for all the attendees to ensure that your phone is on silent mode. And for those who have not yet registered, kindly register at the registration desk at the entrance. Today's lecture is also going to be a conversation, so I would encourage for you to jot down your questions because there will be a discussion session later on. Now to formally commence today's program, may I invite you all to kindly rise for the Tamil Thai Valthu and the Bande Mataram song.
நீராறும் கடலுடுத்த நிலமடந்தை கெழிலொழுகும் சீராறும் வதனமென திகழ்பரத கண்டமிதில் தெக்கணமும் மதில் சிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை நுதலும் தரிதனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம்பியந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே. வந்தே மாதரம் வந்தே மாதரம் சுஜலாம் சுஃபலாம் மலயஜ சீதலாம் சஸ்யஸ்யாமலாம் மாதரம் வந்தே மாதரம் शुभ्रज्योत्स्ना पुलकितयामिनी फुल्लकुसुमित द्रुमदलशोभिनी सुहासिनी सुमधुरभाषिनी सुखदां वरदां मातरं वन्दे मातरम् वन्दे मातरम्.
Kindly be seated. As is tradition, to light the lamp, I would like to invite on stage Professor Jeffrey Ullman, Professor Shanti Pavan, Professor Preeti Agalyam, Mr. Vinod and Ms. Hema from the Office of Global Engagement. Thank you to the dignitaries. Now to give you a little insight on what today's program is about, the Eminent Speaker Lecture Series is a flagship initiative of the Office of Global Engagement, IIT Madras, envisioned to significantly enhance the Institute's global academic presence. Through this series, IIT Madras hosts globally acclaimed leaders, Turing Award winners, Nobel laureates, pioneering researchers, and distinguished personalities, providing a platform for knowledge exchange and inspiration for students, faculty, and the wider community. Today's lecture marks the 4th edition of this prestigious series, and we are privileged to host one of the most influential computer scientists of our time. So to formally begin today's proceedings, may I please invite Professor Preeti, Advisor at the Office of Global Engagement and former Director of IIT Madras Zanzibar, to deliver the welcome address.
Thank you, Renee. It's such a pleasure to be here. Good evening, all. It's great to see such an enthusiastic gathering of students, faculty members, researchers, and guests this evening. It gives me immense pleasure to warmly welcome each of you to the 4th edition of the IIT Madras Eminent Speaker Lecture Series. The Eminent Speaker Lecture Series was born of an urge to open doors to curious members of the wider Chennai community to the scientific world of IIT Madras. In particular, for the young members of our audience today, the chance to listen to, learn from, and interact with the absolutely stellar scientific minds from across the world is, we thought, invaluable. We are glad that we are able to bring these opportunities to you through this series of talks by world leaders. The goals of this series are simply to inspire young minds, to enrich our academic environment through diverse global perspectives, and to encourage thoughtful dialogue that helps us grow together as a community. Over the years, this series has been privileged to host several distinguished speakers whose visits have left a lasting impression on us. In 2023, we had the honor of welcoming Dr. Carl Henrik Helden, Chair of the Nobel Foundation. In 2024, the series featured Dr. Brian Kobilka, Nobel laureate in chemistry, and Dr. Subir Sachdev, recipient of the Dirac Medal and the Onsagar Prize. Each of these lectures sparked engaging discussions and reinforced IIT Madras' strong commitment to academic excellence and global engagement. It is in this inspiring tradition that we gather today for the 4th lecture in the series. We are deeply honored to welcome Dr. Jeffrey Ullman, a towering figure in computer science whose contributions to areas such as algorithms, automata theory, databases, and compiler design have shaped the very foundations of the field. As a teacher, researcher, and author, his work has influenced generations of students and scholars across the world. And we fully expect today's talk to leave an indelible mark of inspiration on all of you. With that, I'd like to again welcome everyone on behalf of the Office of Global Engagement and IIT Madras. Thank you, Nandri.
Thank you, Professor Preeti, for that warm welcome. May I now invite Professor Shanti Pavan, Director in charge of IIT Madras, to deliver the presidential address.
Good afternoon, everybody, and a very warm welcome to young students, faculty members, researchers to this event organized by IIT Madras. It's a pleasure and privilege to have with us today Professor Jeff Ullman, who's the nice thing about trying to introduce Professor Ullman is that he needs no introduction at all. I already saw a whole bunch of students getting signatures, getting their books signed by Professor Ullman. I don't think there's any computer science student who's not gone through their programs without going through his textbooks and his foundational work in the field of computer science. So without any further ado, I request Professor Ullman to come and give a talk. Thank you.
Thank you, Professor Shantipapan. Professor Ullman, if I might just introduce you before you begin.
Okay.
Is that fine?
Right.
Thank you. So, ladies and gentlemen, it is my distinct honor to introduce our eminent speaker. Professor Jeffrey D. Ullman is a Turing Award winner and Professor Emeritus of Computer Science at Stanford University, a globally renowned author in algorithms, compilers, automata theory, and database system. Professor's seminal textbooks have shaped generations of computer scientists across the world. His contributions to the theoretical foundations and practical applications of computer science have left an indelible mark on academia and industry alike. Despite his towering achievements, Professor Ullman is admired for his clarity of thought, his simplicity of explanation, and deep commitment to education and mentorship. Today, Professor is here to deliver a lecture titled Big Data Algorithms That Are Not Machine Learning. Ladies and gentlemen, please join me in giving a warm round of applause as I invite Professor Jeffrey to the stage.
Thank you.
To honor Professor, I would also like to invite Professor Shantipapan and Professor Preeti to hand over a bouquet and the shawl to Professor Jeremy.
Well, hello everybody. That was exciting. Okay, so let's see. Oh, there we go. Oh, my slides are here. I'm gonna, of course, I have to read my slides as I'm going along, so I'm gonna have to sort of stand here so I can get them now. As it says, look, without taking anything away from machine learning, which I think we all know has become a very important part of, well, almost every discipline. But I want to talk about four different algorithms, they're listed here, that are not machine learning, but yet are very important and I think have good applications in the big data field. So let's see. Before going on, I want to invite you to read my book with Yuri Leskovich and Anand Rajaraman, who, by the way, was a graduate of IITM. I don't feel at all, and no compunctions about selling the book because it's in fact free, and you can get it at this URL. Okay, the first story of locality-sensitive hashing. This is it's a very interesting and powerful tool. It's used in many fields. For example, the BLAST algorithm in genetics is actually an instance of this idea. I don't want to talk about the general idea, which actually is very, very broad and has many different byways and interesting cases. I just want to give you a little taste of this. Okay, so anyway, it's sort of magic in a sense, in that you can find, you take a large set, millions, billions of items, and you want to find the pairs of items that are similar in one of many senses, but you want to do it without comparing each pair of items, because that's that's n squared comparisons, and if n is a million, the number of pairs from a million items is roughly 500 billion. It's just way too much to do. But in some cases, there's a very obvious algorithm, and I'm going to, if the notion of similarity is an equivalence, then you can. There's a very simple way to do it. Just for example, let's say that cards are similar if they have the same rank. So that, for example, all the aces are similar to each other, all the deuces are similar, and so on. So that's well, it's very easy. All you have to do is create a bucket for each rank, and when you have some set of cards, perhaps not the whole deck, but whatever you have, you throw them into the bucket that corresponds to the rank of the card. So all the aces go into the first bucket, and the deuces into the second bucket, and so on. Yeah. Okay. Now, in most cases, your notion of similarity will not be an equivalence relation. So if you do that, then the idea of throwing the elements or the items that you're trying to sort out into buckets, it doesn't really work. Okay, so just take an example. If you want to say that cards are similar if they're either the same rank or the same suit. Okay, well, if you want to throw everything into buckets, let's say the ace of clubs would have to go into the same bucket as the ace of hearts, and the ace of hearts is also similar to the four of hearts, say, and therefore you'd have to put the ace of clubs in with the four of hearts, and they're not really similar. So if you think about it, the only way to arrange the buckets so that every similar pair is in the same bucket is to have a single bucket. Just throw them all in there, and then the work of sorting out which of the pairs are actually similar is a quadratic process. And again, just quadratic is just way too much to do. Okay, so in this case, though, there's a very simple workaround. I'm going to do two separate hashings into buckets. Okay, the first, we're going to throw the cards into 13 buckets according to their rank, and then we're going to do another hashing, put the card, or copies of the cards, if you will, into 4 buckets, 1 bucket for each suit. It's important to remember that now the cards are placed in every card's in one of the purple buckets and also in one of the green buckets. So now all we have to do is, well, there's 17 buckets total. It turns out that if cards appear together in any one of those buckets, then they're similar, and every similar pair will appear in one of those buckets together. Okay, so this is a cute trick of having several different hashing functions, but things get even more complicated. Remember, similarity is a very vague term. I don't want to tell you exactly what I mean by similar, because it just varies from application to application. But there are still two things special about this pair of hashings that I did. First, it guarantees that if two cards are similar, they will appear in the same in a bucket together. So we can discover them all. And moreover, every pair that appears together in a bucket happens to be similar. Okay. Now, in a more general case, we're going to use several hashings, but the things, though, they're not quite as simple as it was for the cards example. First of all, sometimes we'll throw items into the same bucket, but they're not actually similar. So we have to look inside each bucket and then run the test for similarity on the pairs in that bucket. Okay. And moreover, it's possible that items are similar, but just somehow never manage to get into a bucket together. So you get what are called false negatives. They're similar, but you never see them. Now, in general, the more work you do, that is, the more different hash functions you use, the more work you do, the more pairs will have to be examined to check whether they're similar, but the fewer false negatives you will get. Okay, so it's an art form and a trade-off that you need to work out. So the general idea is you need to invent hash functions that have that somehow favor similar pairs. That is, if items actually are similar, again, whatever similar means, then they have a good chance of winding up in the same bucket. If they are not similar, then they have a much smaller chance of winding up in the same bucket. Okay? And again, as I said, the goal is you don't want to do too much work, you don't want to hash too many times, you don't want to have buckets that are too big, so you wind up actually having to look at only a small fraction of all possible pairs. But at the same time, you want to cut down on the false negatives. You can in general, you can't get the false negatives to go to zero, but you can make them as small as you like by spending more time and doing more work. Okay, so I want to tell you about now a particular real problem. It's called entity resolution, and you have let's say a set of records. The records each record describes a certain person. Think of it as a transaction record in your bank, or use of a credit card, or something where you need to identify the person involved. So each record would have fields like, I'm going to assume they are name, address, and phone number. Okay. And this is supposed to identify, let's say, who made a charge on the credit card. And what you want to do, given a large collection of records, is to find which records refer to the same person. Okay. Now, this is it's tricky. I think we'll go back for a second. Yeah. Okay. First of all, if two records have the same name, there is a good chance that they refer to the same person. But they might not. There are people who have the same name but are really different people. But it does meet the criterion that I needed, that says if the records go into the same bucket, that is, they have the same name, then there's a better chance that it's more likely that that records with that refer to the same person will have the same name and will therefore go to the same bucket than if the records have different names. Now, there are two problems. One is, yes, when you throw records with the same name into a bucket, they might be different people that just happen to have the same name, but they've got different phone numbers and different addresses, and therefore you'll figure it out when you actually go into that bucket and check. But also, let's say the simplest case, there might be a typo. So it's supposed to be the same name, but there's a letter different or something. Okay, and therefore they would go into different buckets. So, there's this general idea that if records have the same name or the same address or the same phone number, that it's more likely that they refer to the same person, but there's no guarantee. So there's just a lot of randomness in this whole story. And then, as I said, a set of a million records, if you do it the naive way, where you just compare every pair of records and see if they look like they refer to the same person, you've got roughly 500 billion pairs to look at, and if 1 million records isn't enough, credit rating agencies, they're getting records of transactions from all different banks and credit card companies and mortgage companies, all sorts. They deal with all sorts of records about your financial transactions. There are hundreds of millions per day, and they have to sort them out correctly, because you don't want to get a charge that is by someone with the same name but isn't you. You don't want that put on your account. Okay. So as I said, we'll do one hashing where we just hash all the records by name. Okay. And then we're going to do another one where we hash all the records by phone. And let's say a third one with address. And again, the idea is, you hope that if two records represent different people, then they won't agree in any of those three fields. And therefore, they'll never appear together in a bucket, and therefore you'll never have to even deal with the question of, do these records represent the same person? That's the big savings. That's the magic of locality-sensitive hashing. The idea that you avoid ever even considering most of the pairs of records. But on the other hand, just because two records get sent into the same bucket is not a guarantee. Okay, and then there are all sorts of reasons. I've listed a couple that as I said, different people can have the same name, or you might have you had a phone number, you gave up that phone, and it gets assigned. The number gets assigned to somebody else, and the big one really is that people entering the records will make a typo. They'll change one of the digits in your phone number so it looks like it's somebody else's phone number. Okay. So anyway, just to summarize the algorithm, you use various fields like name and phone or address, and you hash all the records into buckets several times, one for each of the fields that you're using. And then you go into each bucket and you compare what we assume will be a very small fraction of the total number of pairs, because you only look at pairs if they appear in one of the buckets together for one of the different hashings. You know, but unfortunately, it is possible to have false negatives by this scheme. For example, two records, they should have the same name, the same phone number, and the same address, but there's a typo in each one of those fields, in one of the records. So they never go into the same bucket for any of the hashings, and therefore you never even consider the question, are these representing the same person? Okay. There we go. Okay, new topic. It's the problem of counting distinct elements in I think of it as a stream, a big sequence of items where you might have repeated elements. So you can't just count the length of the number of elements. You have to count. You only count an element if it's the first time you've seen that element. So, a good example would be, let's say, Facebook wanting to know how many unique users it has this month. Okay. So many people will log on several times. You only want to count them once. Okay, so you think of it as a stream of Facebook logins. Okay. Well, I mean, there's an easy algorithm to do it. You maintain a hash table with the element. Well, I think I'll tell you. Come on. Yeah. Okay. You're going to keep a hash table of the set of users that you have seen. Okay. And you also keep an integer account of how many different users you've seen. And then a new login comes in. You hash the Facebook ID, and you see if it's in the table. If it's not in the table, then you put it in the table. So you to intercept the next time that person logs in, and you increment the count by 1. Okay. On the other hand, if the login is already in the table, then you do nothing. Okay, you don't increment the count in particular. Okay, so this uses a lot of space. Now Facebook can afford it. I mean, we're talking about maybe they have 3 billion users or something like that. So probably a terabyte, a hash table a terabyte in size would do. But for Facebook, that's nothing. So that's fine. But I want to give you another example, a little more complicated, where the hash tables themselves are fairly small, but there are way too many of these hash tables to store in memory. Oops. Okay, yeah. Okay, I want to talk a little bit about web crawling. Okay, that is the thing, let's say, that Google uses to find all the pages out on the web, and it makes copies of them and process it so it can answer your Google queries quickly. The trouble is, even the web is too big even for Google. Okay? So they can't catalog every page that actually exists out there. So they might do something, like they're going to start from one or several starting points. For example, I think they actually use the home pages of universities distributed around the world. And then when you crawl the web, what you do is you go to a page, you extract all of the links on that page, if there are any, and you put those links on a list to explore the pages that are pointed to, and eventually each of those pages will get to the top of the list, and you will do the same thing with that page. That is, you'll read it and find all the links within it, and put those links on a queue of pages to crawl, as it's called. And by the way, this is going to be done not by a single processor, but by many, many processors who are out there crawling pretty much independently. And as a result, one of the things that can happen is that two of these crawlers could wind up in the same space where they're actually crawling the same pages. Don't worry about that. Okay, at any rate, you might think again that you can get to the entire web that way, but in fact the web is too big. So what they actually do is they'll follow hops, as they call it. By hops I mean you look at a page, find a link within it, and then look at the page that's pointed to. Okay, so you might follow it for maybe 12, 13, 14, maybe 15 hops. Okay, and you get to many, many pages. Probably multiple trillions of pages will be reached that way. But at some point, you have to start being a little bit more selective, and because the pages that you're finding now, that where the closest way to get to them from some page like a university homepage is 15 hops. These are very rarely interesting pages. Okay, so you have to cut it down. Now they don't just say, okay, 15 hops and that's it. But they start being a little bit more judicious. They will now only put a page on a list to be crawled if it has a lot of predecessors. This is the original intuition behind Google was what they call PageRank, which sort of says that pages are important if there are lots of ways to get to them. Well, this is counting the number of predecessors is a hint. It's not exactly PageRank, which is much too complicated to. You can't do it on the fly anyway. You have to have the whole web in front of you before you can compute the PageRank. So we're really just going to look for pages that have a large number of predecessors that you've already crawled. And, well, as it says, okay, you're looking really for an approximation to the PageRank. That's the number of predecessors that you've found. Okay, what we're going to do is make a compact representation of the set of predecessors, so that we just want to start with the count of predecessors. We don't care what the predecessors are. We just want to know how many different ones there are. So it's another one of these count distinct problems, where you only want to count a predecessor once, even though you may have found it several times. Because you've got these hundreds of crawlers out there, and several of them may find the same predecessor of a given page. Okay. So what we're going to get is an approximation to the count, and this same story as with the locality-sensitive hashing. The more work you do, the more time it'll take, the more space you need, but the more accurate your counts will be. But in this case, really an approximation of the count's okay, because the count itself is an approximation to the PageRank. So anyway, we want to do we're happy to do an approximation of the count. We pretty much have to, because if you have trillions of pages and each needs a hash table of 1,000 bytes or something, that, even for a company like Facebook, that would be too much. You could not do that. Okay, so, again, what we want to do is estimate the count by just storing a very small number of bits. Again, it's another one of these what should be familiar stories. The more effort you put in, the better or more accurate your result will be. But the error never goes down to zero. Okay, so what we're going to do, we're actually going to create a large number of hash functions. But I want to start off by telling you about how I create one of these hash functions and what I do with it. Okay, but remember, the whole process is going to have could be several hundred different hash functions. So we take the hash function h. Well, all we need to know is that if there are n elements, it hashes to at least log base 2n of bits. Okay, for this hash function h, for each element, for each element a, when I hash a, that is, when I compute h of a, when I compute h of a, there will be some number of zeros at the end of that hash function. Okay, it's a stream of bits. It could be zero, but I'm going to let little r of a be the number of trailing zeros in the hash value of the result you get when you hash a. That's called the tail length. So, for example, 0000101 has tail length 0 because it doesn't end in any zeros. And 101000 has tail length 3 because it ends in 3 zeros but not 4. And then I want cap r will always be the maximum tail length r of a that I've seen for any a that I've found in the stream so far. Okay. And basically, for this hash function, all we're going to do is record capital R, just that maximum tail length. And look, if the tail length is incredibly long, like 31 bits, 31 zeros, well, that's great if you're mining Bitcoin, but it will not be important even. I'll show you. You're going to see why. But tail lengths that large are going to be ignored anyway. So let's say 5 bits is enough to get you up to cap r equals 31, and probably 4 bits, which would let you get to cap r equals 15. That is a tail length of 15. That's pretty much okay for every reasonable application. So what we're recording for each hash function is just a few bits, say 4 or 5. Now, that hash function will lead to an estimate of the number of the number of distinct elements that we've seen. And the estimate we're going to use is 2 to the r. Now, again, remember, there are many different hash functions. Each one will give you a different r. So we're going to have to combine those r's in some way. But the idea is that even if we had just one hash function, why would 2 to the r be a good estimate of how many different elements you had seen? Well, if you look at it this way, if you've actually seen 2 to the r different values, then there's a good probability that you will have seen one that hashes to whose hash function ends in at least r zeros. The actual probability, if you want to know, is 1 minus 1 over e, or about 69%. Okay. On the other hand, if you've seen many fewer than 2 to the r different values, the chances that one of them hashes to a tail with r zeros is pretty small. Okay, so 2 to the r sort of looks like the right estimate based on a single tail length. The trouble is that's actually nonsense. Okay. And in fact, the expected value of 2 to the r is in principle infinite. And the reason is if you look at larger and larger values of r, the probability, when you add 1 to r, the probability that you will see a tail with 1 more zero is halved. Okay, the probability of seeing a tail of r zeros, it's approximately n. If you've seen n different elements, then the probability one of them has a tail of r zeros is approximately n over 2 to the minus r. Again, I won't go into it, but it's not exact. You'd think it's exactly that, but it's not. But asymptotically, it kind of is. Okay, so. Okay, but so when you increase r by 1, the probability of getting that r goes down by a factor of 2, but the value that would be returned is 2 to the r, so it doubles. So each value of r basically contributes the same amount to the expected value of 2 to the r. Okay, so what it amounts to is if you happen to get a very long tail length, it just skews everything. It gives you an estimate that's just too high. So the way you deal with this problem is, first of all, as I said, we're going to have many hash functions. Think of it as hundreds of hash functions, and therefore you're going to get many sample values of r, cap r, and we're going to combine them. Well, if you combine them, the average, again, doesn't work, again, because of the fact that the expected value of 2 to the r is technically infinite. The risk is, if there just happens to be one very large value, it dominates everything. Okay, and you overestimate how many elements you've seen. You try the median, which has the power that it ignores the really extreme values. Okay. The trouble is, then the median, all of your choices are powers of 2. So the median is going to be one of these powers of 2, and therefore, no matter how many hash functions you use, it would never converge to an estimate that is correct if the true estimate is, let's say, midway between 2 powers of 2, like between 64 and 128, so maybe 100. It'll never converge to 100. It can't do that. Okay, so what you do is we're going to take groups of size about log n, and I think about 4 log n we'll do, and we're going to take the average within each group. Now, again, some of those groups will have one very large value that just skews things, and that's sad. But we'll take the median of the averages, and now you're averaging numbers that are not necessarily powers of 2. They could really be anything reasonable. So taking the median is okay, and the median has this nice property that it ignores really extreme values. Okay. So it's called the Flageolet-Martin algorithm. I should have mentioned that, and it's a powerful tool for estimating the number of distinct elements without using nearly as much space as the obvious algorithm. Okay, so the next story. I want to talk about sampling. Okay, and again, I think of my data as coming in a stream, or it doesn't, but of course it doesn't matter. It could just be a big set sitting there. And I want to, first of all, in many situations, sampling is actually easy and effective. So the problem I want to propose is, what it says here. Google wants to know how many times the query the search queries Taylor Swift was asked in a month. Okay. On the other hand, the stream. By the stream, I mean, of course, the stream of search queries that come into the Google servers. And we just want to sample 1/10 of the stream because we don't want to have to look at the entire stream. Okay, so what we do is we take a random 1/10 of the search queries. We count the number of Taylor Swift queries, and we multiply it by 10. Okay. And if we've chosen we've chosen our sample randomly, that's going to be a pretty good estimate. And again, the bigger the amount of data, the closer you would expect that answer to be. So that's fine. Let's see. Now, here's where things get a little bit trickier. Okay. Now Google wants to find out how many search queries this month were unique in the sense that they were asked only once. But again, we'd like to just sample 1/10 of the stream. Okay. Now, here's the trouble. If you look for unique queries in the sample, the fraction of unique queries in the sample will not be the same as the fraction of the sample in the entire stream. And moreover, there's not even any relationship between the number of unique queries in a sample of 1/10 than there is to the actual number of unique queries in the entire stream. So, for example, if a query happens to be unique in the whole set, then it has a 10% chance of being the sample. But if a query appears twice in the whole stream, it has an 18% chance of appearing looking unique in the sample. And if it appears 3 times in the full stream, then there's actually 24% chance it'll look unique in the sample, and so on. The point is that the fraction of unique queries in the sample doesn't relate to the fraction of unique queries in the whole set, because there are so many of these things that look unique in the sample but really aren't. Okay. Okay, so it turns out, though, that I led you up a primrose path, because that's not really the way you should sample for this type of query. That is, we were picking picking our sample by choosing random positions in the stream. What we should do is pick a random subset of values and examine only those values. That way, that is, we're going to hash each search query, that is each element in the stream, to one of 10 buckets. Okay. And we'll take one of those 10 buckets as the sample. Okay. Okay, and now the nice thing about this is that the sample, which by the way obviously should be 10% of the whole, is that if one instance of a certain search query is in the sample, then all of them will be in the in the sample, and therefore you something is unique in the sample if and only if it's unique in the whole. So you can count the number of unique queries in the sample and then just multiply by 10, just like we did for Taylor Swift. Okay. Well, I might say you can do even more. Suppose you want to say, well, I want to sample 10% of the queries, except that I don't want my sample to consist of more than 1 billion search queries. Okay. Well. Okay. Well, you're going to hash to a larger number of buckets than 10, and if you need to shrink the size of your sample, throw some of the buckets out of the sample. For example, suppose we'd like to have a 10% sample, but if the sample gets larger than 1 billion queries, we want to make it small. We want to limit it to a billion. So we might hash to 100 buckets rather than 10, and we'll take 10 of those buckets, say those 0 through 9, as the sample. But if we need to cut down the sample, the size of the sample, get rid of one of the buckets. Okay. If it's still too big, you get rid of another one. Obviously, this is limited, but if you wanted, if you're really worried about how many buckets you might have to get rid of, start with 1,000 buckets, and your sample will be 100 of them. You can deal with that. Okay. Now it turns out that this technique works any time you can see pairs. You can see the elements in your stream as pairs, a key and a value. Okay. Now, if you know SQL, what it means is the query that you're asking groups by the attributes in the key, but not the value. If you don't know it, just the intuition is the key is the set of attributes where you want all or none. Okay. So in the example I just gave you, the data was simply a key, right? Because you want all or none of the search queries with a given value. Okay. Now again, you hash the key only to an appropriate number of buckets, and you take some of those buckets as a sample. So let me just give you a quick example that I think will illustrate it. My stream data consists of records that are an employee ID, the department they work for, and their salary. And the query I want to ask is, what is the average over departments of the salary range. That is the difference between the maximum and minimum salary of any employee in that department. Now, in this case, the key is department, because I sort of, the way I phrased it, I hope you see that I'm saying we want to look within each department. So we have to group all of the employees by department, okay? And the value is the other two attributes, the employee ID and the salary. Okay, now remember, if you sampled by position in the stream rather than the value of the key of the department, then you're going to miss a lot for each department, you're likely to miss the minimum and the maximum. So this would bias the salary range too low, because anytime you miss a minimum salary or you miss a maximum salary, you get something that's too low, and there's no way you can get a range that's too big for a department. Okay. On the other hand, so the right way to do this is you use the hashing on the department. You're going to pick some of the departments and not others. So the sample will be a set of departments. You can look inside for each department. You know you have its minimum and maximum salary, so you can correctly compute its range. So you then average, for the departments in the sample, you average that salary range to get the answer. Okay. So the last thing I want to talk about is an algorithm for finding triangles in a graph. And, the key idea is something called heavy hitters, which are, in terms of graphs, they're nodes that have a high degree, that connect to a large number of other nodes. That turns out to be the important idea. Motivation, I always feel like I have to give you some motivation, but okay, it's all coming out. Okay. One of the people have been working on notions of communities in social networks for a long time. One of the original things that they discovered was that as communities age, they tend to bring people together, and therefore sort of everybody in a community becomes friends. So you can measure the age of a community by counting the number of the density of triangles. How many triangles in the graph is friendship, the friendship graph. That is, the nodes are Facebook users, and the edges are pairs of users that are friends. Okay. The algorithm I'm going to talk about is actually a special case of a very interesting result that was discovered, I think, about 10 years ago. Turns out that in order to optimize queries in a database, you really need to know about these heavy hitters. And the question, again, if you don't know anything about databases, I hope this will make sense. Anyway, that if there's an edges relation, that is, the edges of AB is true if and only if A and B are connected by an edge. And to say that there's a triangle for nodes, if nodes A, B, and C form a triangle, what you have to say is that there's, edges of AB is true, and edges of BC is true, and edges of AC is true. So that's really a join. It's a query for triangles. Now, again, it turns out that in order to optimize queries like this, you have to think about, again, this heavy hitter notion. That is, you have to distinguish values that appear frequently from those that do not appear frequently. Okay, so again, I want to give you algorithms for finding triangles and doing it optimally, fast, that is. And I want to set up a data structure which is not really very deep. We'll simply, we want to know that in constant time, we can tell whether or not an edge exists in the graph. There's given two nodes, are they connected by an edge? And for example, a hash table, just hash all the edges. That's expected time, order 1. But there's another thing that we have to do though. Given a node, we want to be able to find all of the adjacent nodes, that is those that are connected by an edge. In time, it's proportional to the number of those nodes. And there's a simple way to do that. Just for each node, make a linked list of all its adjacent nodes, those that are connected to it by an edge. Okay, so a little notation. I want to say the graph has n nodes and m edges. Notice that m can't be bigger than the number of pairs of nodes, which is n choose 2, which is a little bit less than n squared over 2. So m is certainly less than n squared, and that's important. Well, let's say the obvious approach to finding the triangles, maybe, is let's just do a triple loop. We'll loop over all sets of 3 nodes. And we'll use that hash table to test whether there's an edge between each 2 of those 3 nodes. And so that's going to be an order n cubed algorithm, right? Because you have roughly n cubed over 6 triples of nodes, and you're going to do constant amount of work for each one. Well, here's actually a better method is, in fact, to loop twice, once over edges, E, and then once over nodes, U. And then all I have to do is use that hash table to test whether the 2 ends of E have edges to U. And if so, you've got a triangle, otherwise not. And that's an order m times n algorithm, because you're looping once over an edge, all the edges, that's m times. And then for each edge, you're looping n times over the nodes. And since remember, m can't be bigger than n squared, and is usually somewhat less, so order mn is always better than n cubed, or at least no worse. Oh dear. I know what's happening here. Yeah. Oh darn. This display is too wide. So I'm going to have to explain to you a little bit what's going on here. Okay. Again, we're going to use the idea of a heavy hitter, which in this case, we'll say a node is a heavy hitter if it has a degree at least, this should be square root of m. Okay? It's at least square root of m. Now, one thing that's important is you can't have too many heavy hitters. Remember, each edge contributes 1 to the degree of 2 different nodes, so the sum of the degrees in any graph is always twice the number of edges. Okay, so if you had more than 2 square root of m heavy hitters, each of them has at least square root of m degree, you'd have a sum of degrees just from the heavy hitters that's bigger than 2m. So you can't have that. So the number of heavy hitters has got to be limited. So then what do? first thing we're going to do is going to consider all the triples of heavy hitters. That's the first algorithm that I told you about, but only for the heavy hitters. And for those, we're going to see if there are edges between each pair of those three. And I claim that this is an order m to the 1.5 algorithm. Again, since there are only 2 square root of m, there are at most 2 times square root of m heavy hitters, and you know, and therefore the number of triples of heavy hitters can't be more than 8 times m to the 1.5. And then it's, of course, for each of those, for each triple, it's a constant time to see whether there's a triangle among them. So it's an order m to the 1.5 step, but this only handles the heavy hitter triangles. And what about the others? Well, in all the other triangles, at least one of its nodes is not a heavy hitter. So all we have to do then is look at all the edges, E. Let's say E is an edge. First of all, if both ends of E are heavy hitters, then we're just going to ignore it. But if one or both of the ends of E are not heavy hitters, we'll pick one of them. Doesn't matter which one. And remember, okay, so let's say we'll use node U from which is not a heavy hitter, from the edge E, and then all we have to do is look at all the nodes connected to U, and there can't be too many of them. There can only be square root of m of them, right? Because AU is definitely not a heavy hitter. And then we just want to see whether V is connected to the other end of the edge E. And so that's another order m to the 1.5 algorithm, again, because there are at most m edges, or there are m edges, and for each one of them, because we only look at an end that is not a heavy hitter, we can just go down the list of adjacent nodes V in time square root of m, so the whole thing is m to the 1.5. Okay, so you've got 2 parts to the algorithm, both take order m to the 1.5, and then it turns out that that's the best you can do, because given any n and m, you can find a graph that has n nodes, m edges, and some constant fraction, at least, of m to the 1.5 triangles in the graph. So no algorithm can do much better in terms of the parameter m. And you know, I think should be obvious, again, because m is at most n squared. M to the 1.5 is never worse than n cubed or mn, and if the graph is sparse, that if m is much less than n squared, then m to the 1.5 is really much, much better than either of the 2 obvious algorithms. Okay. I'm not going to tell you how to do this, but if you want to count the number of triangles rather than enumerate them, you have to avoid double counting, but I'll let you figure out how to do that. Okay, thank you. That's the story. Okay, let's see. Get out of the light. Well, yeah, ask me anything, I guess.
I think we can give Professor another round of applause, everyone.
It's okay.
Thank you, Professor Ullman, for your insightful lecture. I hope today's lecture gives us much to think about, and it has generated curiosity which will go beyond this hall into your classrooms and research spaces. We will now open the floor for the Q&A session, for which I would like to invite Professor Dr. Aishwarya as the moderator. So this is a space for curiosity. Please keep your questions concise, and you may ask for clarification or challenge respectfully. Kindly raise your hand so that our volunteers can assist you with the microphone.
So, are there any questions from the audience? Yes, I see a hand over there.
I do not.
Hello, Ullman. So I have a question regarding whether can we use these heavy hitters to create indices in graph databases, since it allows us to find out the nodes which are accessed frequently.
Are you talking about the last?
Yeah.
The last one. Yeah. Yeah, it's actually been done. Yeah. Yeah. Again, what I gave you was just a very simple example of this general technique for optimizing queries on graphs, and it has been done. In fact, a former student of mine at the University of Waterloo just did a little startup on doing exactly that. Yeah. Again, it's been pretty much worked out. Yes. You can.
Thanks for giving me the opportunity, sir. And thanks for the compiler book.
Well.
Other questions? Yes, there's a hand over there.
I'm sorry, I can't actually see what's going on.
So, hi, Professor. So, everything that we do in this world is basically an algorithm, and machine learning is also an algorithm, and they are trying to basically create an algorithm that creates itself. So, why don't we position it in this way? Machine learning is also a type of an algorithm, right?
I agree, yes.
So, do you think is it possible for creating algorithm that creates every algorithm, basically an AGI?
Probably violates Turing's theorem, but first of all, I don't see machine learning as learning anything. It used to be. In 1990, when you talked about machine learning, you were really talking about algorithms that improved themselves as they went along. Okay? That's not what machine learning is really about. Machine learning is an algorithm, today, is an algorithm that builds a model of data. Okay? And that's all it is. Okay? These models, the things like these deep neural networks and decision forests, there are all kinds of models that turn out to be very beautiful and powerful. Okay, but they're just plain old algorithms. They're not learning anything, and they're not addressing their own composition in the way, again, people in 1990 imagined machine learning would be. Okay.
Yeah, so you mean that human intelligence is not something we could categorize as an algorithm?
Well, the whole intelligence, no, any more than a computer is not an algorithm. It's a device for executing algorithms. But just like people are.
Okay.
I get the feeling I'm not really addressing your
Yeah,
your concern.
my whole question is regarding the AGI development. So they are having this kind of mentality that if we are able to figure out the algorithm, basically it's equivalent to Einstein's unified field theory. So if we could map an algorithm to map other algorithms, basically we could solve the intelligence and we could move into singularity. So that's the whole idea behind Demis or Dario or any other people out there in the field. So they are curious and pursuing that. But is that really possible, or is it kind of like an imagination or like a quest of a North Star?
Yeah, I don't know. I suspect very much that it's not going to get anywhere. That it again it probably there's probably a logical contradiction. Like Turing's proof that there's no Turing machine that can tell whether another Turing machine is going to halt or not. There's probably no algorithm that can build all other algorithms. Because I don't know otherwise. If you could build all algorithms, then it could build an algorithm that would stop it from building algorithms or something like that.
Yeah,
You know.
then what is the program regarding to the Institute of Humanist Intelligence in Stanford? These companies, corporates are trying to build this kind of an algorithm. Then what is humanist intelligence is trying to build out in Stanford?
I'm not aware of that at all. If so, I'm sort of ashamed of my colleagues. That's all I can say. Really. I mean, if you're talking about the human-centered AI center, I mean, they're doing real stuff. But they're not crackpots. But I doubt very much that they're trying to violate the Turing's theorem on this.
Yeah, so basically.
So, yeah, okay, maybe last question so that we can give others an opportunity as well.
Yeah, so basically humans are not meat binding computers. That's what you are coming to say. And cognition is not an algorithm.
Wait, I'm sorry, what is not an algorithm?
Cognition is not an algorithm.
Cognition is
the
not an
human
algorithm.
cognition.
Yeah, no. Again, cognition is a process. It's like running a computer is not an algorithm. The things that the things that the computer can do while it's running, those are algorithms, and the things that you can think about while you're thinking might be an algorithm. Yeah.
Okay.
Thanks. Yeah. Other questions?
Yeah,
Over there.
I had a question here on this side. Yeah, so
I'm sorry.
here.
Wait, I'm sorry. The lights are making it impossible for me to see anybody.
All right.
But okay.
Yeah, so today, I mean, primarily I've used hash functions before in both cryptography as well as hash tables, as in studied what properties are required for use in both use cases. So here, since we are using it in sort of a different way, it seems to me that many of those properties are either not required or even detrimental. So in the sampling algorithm stuff, what is the kind of hash function that we would want to design? Let's say typically we would use it on like a JSON document or something.
You mean, I'm assuming that the hash function generates completely random values. Okay.
Yeah,
but,
so in practice,
but there are many hash functions that will do a good enough job.
Okay, so in practice, the same ones that we use in hash tables and stuff would work here.
Yeah, I mean, I mean, you can, there's a hash table primitive in Java and probably Python and all of these languages these days. They'll hash for you, and that's undoubtedly good enough.
So even like in most hash maps, you have linear addressing among 8 to 10 items. So all of that works fine for these use cases as well?
Again, I never worry about it. To me, just I'll just call for a hash function and somebody will provide one that's good enough. Admittedly, there are hash functions that don't quite work, but we've probably learned to avoid them. And in each of the applications of hashing that I gave you, just something that looks random is good enough.
Question over there.
Hi sir, how are you?
Hi, I'm doing okay. How are you?
I'm fine. So my question was, I wanted to know your opinion about LLMs getting saturated. I mean, the models have gotten smaller. They basically said the amount of data we needed has to get bigger to reach better performance. GPT-2 was 350 billion parameters. So now we are able to do more capable models in around 20 billion, and it's getting lesser as we speak. So is this really the way to go? Is it going to move towards the millions, or are we going to pivot to reinforcement learning or anything else like that?
Okay. Well, let's see. I'm hearing two issues. One is, can you build better LLMs with more data? Right? And the answer is probably, but I don't know where the data is going to come from, because we've already sort of found all the data that's digitally represented. And then the question of, there's a general tendency, the field of machine learning, and LLMs really are just deep networks in some way. They do try to reduce the number of parameters, that is, build smaller models. Whether you can have a competitive LLM with the number of parameters in the millions, probably not. Just because there are just too many ideas out there. And if the LLM is going to be able to converse about pretty much any topic you desire, I would find it kind of, it doesn't, that seems a little too small, just given how much, again, just how many thoughts are entailed in the web. But I could be wrong. I really have not thought much about that.
So about reinforcement learning, is it really the way to go? I mean, they found it really unoptimized at the very beginning, but now I feel like there are some developments over the course. So could that be it?
Yeah, there are some applications where reinforcement learning works, right? And and somewhere it's, you use something else. What can I tell you?
Yeah, that's true. Yeah. That will be. Thank you, sir.
No, sorry.
Other questions? I see a hand over there. Yeah. Over there, right next to you.
Hello. Greetings, Professor. Can I?
Okay. Hi.
Sir, my question is that suggest us few fields where we can focus our research on and that LLM and AI kind of success.
Could you repeat that? It's, I'm not quite getting it.
Sir, I request you to suggest us few fields where we could focus our research on and that LLM and AI are weak at.
Okay, you want some suggestions for research topics using LLMs or?
Where LLMs and AI do not perform well, if I understand correctly.
Yeah.
Well, look, I mean, people are going to be using LLMs I mean, it looks like the next stage in the evolution of LLMs is going to be what they call agents. Okay, you take the LLM, but it knows how to talk about things, but it doesn't know. It doesn't have information relevant to a particular subject. So. So again, you go through a process that looks very much like machine learning. You train the LLM, right, to do a particular task well. Okay, and it looks to me like there are just a very large number of different applications where you could build something. You take an LLM. You train it to deal with a domain, and so that's certainly a fine field. I don't think that the old machine learning issues are dead yet. I think people are. Not every application has to be LLM based. There are other algorithms like not only other machine learning algorithms, but the kinds of things that I talked about today. These, I mean, I guess what I talked about is more issues of efficiency than capability, but again, what can I say? There are lots. If I were, let's say, to advise a student to find a thesis topic, I'd say find an application you're interested in and see if you can use LLMs or machine learning technology or something to do better than it has been done.
Yes, thank you, sir. But I also need you to suggest me few areas where LLMs and AI don't interrupt us in the future.
I'm sorry, what LLMs don't do what? Don't
interfere with our jobs and works in the future, so that we can focus more on it.
You're asking for specialization that you can do such that your job will not get taken over by AI?
Oh. Yeah. Is that your question?
Yes, that seems to be his question.
Yes.
Yes, sir.
Oh, okay. Well, computer programmer is not going to be taken over. Okay. I think there's no question that you're going to have to be using LLMs. If you're going to be a software engineer, you're going to have to know how to do what they call vibe coding. And there may be, you will be more efficient. The thing I always come back to, I lived through the transition from assembly language to high-level languages like Fortran. Okay. And yes, I became much more efficient, but there was also so much more work to do that the demand for programmers went up, not down. Okay. Now, maybe, I have a friend, for example, who says, well, we already code everything we need to code. So if programmers become twice as efficient, we really only need half as many programmers because there isn't anything more to do. That probably isn't quite true. Okay, there may be some contraction in the number of programmers that are needed, but But that's not going away anytime soon. And I've also seen numbers that sort of imply this, that the actual number of computer programmers being hired is it's not, either it's not changing, or the changes are due not to vibe coding but to over hiring during COVID or something like that. You know, again, look, you know, we've seen for decades now, jobs have been destroyed and new jobs have been created. You know, again, when I started out, I had a secretary who would type things up for me, right? Now nobody has a secretary, they type things up for themselves. Okay, but, you know, the people who were secretaries found other jobs, and you know, other functions became available. We do more. We're basically able to do more, you know, with technology, and that itself creates new jobs, new, you know, functions that we didn't even have before. You know, so you know, the recent history says pretty much full employment, right? You'll always be doing something if you're willing to adapt, either adapt new technology or move to another job. You'll be employed. You know, and you know, I guess I also think that it may be time to make work less demanding, right? You know, for many years, it's been sort of norm to you work 5 days and you have 2 days off. Maybe people should work 4 days and have 3 days off, or work 2 days and have 5 days off. I don't know. You know, I mean, again, the history of the world in general has led, you know, you see the fraction of your time that you spend at work has been going down. Okay? And part of that is due to the, you know, the Industrial Revolution and the introduction of machinery that did part of your job for you. I don't know. You know, I wouldn't. I just, you know, I wouldn't worry too much if there's something you see you'd like to do. You know, go for it. And you know, I was listening to, I think, the head of the Lyft, the car company. It's Uber, I guess. You know, they're introducing driverless cars, but he says, you know, most people are going to want a human being to drive the car, right? Help, you know, the driverless car can't help you with your luggage, for example. And he says, you know, he predicts that 10% of the rides will be in a driverless car. You know, but you know, maybe that's pessimistic. I don't know. You know, but don't panic. You know that the world is coming to an end because of LLMs or any other technology, robotics or anything like that.
Yeah, thanks. A question over there.
Good evening, sir.
Hi.
Sir, I study in grade 11. So I would like to know the difference between these big data algorithms and machine learning, and which, in your opinion, is more preferable?
Well, neither. I mean, it depends on what you're trying to do. Okay? You know, locality sensitive hashing, say, is not a machine learning algorithm. So if you're actually trying to find similar stuff in some sense, you got to use that. You can't just, you know, build a neural net to do it. You just gotta know what your problem is, and then you know, use the best method that you know that's available for it.
Thank you, sir.
I guess we are coming towards the end of the program. Maybe one final question. Okay.
Hello? Just a minute, I'll just...
Professor Ullman, at the back.
Sir?
At the back.
Good evening, Professor.
Okay. Locating. Hi. Okay.
Good evening, sir. Sir, I have a small question. So you explained elaborately about the heavy hitter pattern that you had explained. So it was really amazing how you optimized the solution from O of n cube to O of m power 1.5. So I was thinking whether is it useful in maybe detecting the cycles in the graph, or would it be using an approach of minimum spanning tree like in the prims or the Dijkstra's? So what field would your heavy hitter approach come in?
Okay, well, again, the answer is that was just a small sample. Anything that you can express as a join of relations. Okay, and again, if you don't know what a join is, it's a, when you join relations, you find the relations have columns, and columns have names, and you find rows or tuples of the relations that agree in the columns that have, of the two relations that have the same name. Okay. Again, you know, the example that I gave was A, B, and C are nodes. If I have edges of AB and edges of BC, then I want to find those edges that go from A to B, and then there's another edge from B to C, and that gives me, it gives me a path, ABC, and then to make it a triangle, you have to check that there's also an edge from A to C. Okay, so that's an example of a join. And again, it turns out any join of relations whatsoever has an optimal algorithm. In many cases, the optimal algorithm involves breaking down breaking down the rows of the relations according to how many times the values in those rows appear in the entire database. And it's a again, it's a very complicated theory, you know, but it has been worked out, and it applies to absolutely any join. Like if you want to find squares instead of triangles, or in any shape, any shape of subgraph within a graph, it's always expressible as a join. And in most cases, the optimal algorithm does involve separating into heavy hitters, or even more levels of counts of numbers of times that things appear.
Thank you, sir.
Okay.
So I'll invoke moderator privilege and ask you the final question.
Okay.
So there are many school kids in the audience. Do you have any words of advice for them as they embark on their future career?
Oh, well, sort of, School kids, yes, I was told that there would be
Maybe you could
middle
raise your
schoolers.
hands,
God,
people from various schools.
I hope you got something out of this, because it's and so stay in school, don't do drugs. No. But you know, seriously, I hope you have a great opportunity to keep going with your education. The further you go, the better your life will be on average. Okay, and I hope that you know you have the strength and the resources to do that. I guess.
So thank you, Professor Ullman, for that enlightening talk and illuminating question and answer session and your motivational words.
Thank you, Professor Aishwarya. Thank you to the audience for your engaging questions and the discussion that followed. Now, we take this opportunity to, as a token of our appreciation, we would now like to felicitate Professor Ullman. May I request Professor Preeti to kindly do the honors.
Do I get to keep this? Oh, that's nice. Very nice. Oh, yes. Thank you. Okay. Okay, thank you. Okay. We done?
You can be seated on the audience.
Wait, I'm sorry?
You can be seated on the audience. You will conclude the session.
Okay.
You
Okay. Wait, I should probably...
To formally conclude today's program, may I invite Mr. Vinod from the Office of Global Engagement to deliver the vote of thanks.
Thank you, Rennie. Good evening, everyone. As we come to the end of the 4th edition of the Eminent Speaker Lecture Series, it gives me great pleasure to thank all of those who helped make this evening both meaningful and memorable. We begin with our heartfelt thanks to Professor Jeffrey Ullman for a truly engaging and thought-provoking lecture. Thank you, sir. Your insights, reflections, and generosity in sharing your journey have deeply resonated with our audience and sparked conversations that will continue well beyond today. We are grateful to Professor V. Kamakoti, Director of IIT Madras, for his constant encouragement and leadership in nurturing platforms that bring the global scholarly community closer to our campus. His support continues to inspire initiatives such as this lecture series. Our sincere thanks go to Professor Shanti Pavan, Director in Charge, for graciously accepting our invite, and Professor Raghunathan Rengaswamy, Dean of Office of Global Engagement, whose vision and steady guidance have been central to shaping the lecture series forum. We also extend our warm appreciation to Professor Preeti Agalyam, former Director IITM Zanzibar and Advisor Office of Global Engagement, for your time and support at every stage. Thank you, ma'am. My special appreciation goes to Professor Aishwarya from the Computer Science Department of IIT Madras for moderating the Q&A sessions. Thank you, ma'am. We thank our faculty members for their presence and insightful engagement, and our alumni for joining us despite their busy schedules and reaffirming their enduring bond with the Institute. A special word of thanks to the students whose curiosity, questions, and enthusiasm truly brought this session alive. Finally, we thank each one of you for being here, for sharing this experience with us. Your presence is what gives life and purpose to initiatives such as the Eminent Speaker Lecture Series. Once again, thank you all. We look forward to welcoming you to many more such enriching conversations in the days ahead. Have a great evening. Thank you.
Thank you, Vinod. May I now request everyone to kindly rise for the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you, everyone. Have a great evening ahead.